Actually, if you do not mind, I wanted to, because I didn't record my video, so I need to go back to recap what I solved in the number 10. So this is an exam number 3, spring 2018, and that's the number 10. And the breeder reaction is a nuclear reaction to make the plutonium. And there is 2 steps of reaction that is shown. And they ask you what is a species X and what is a species Y. And the first X is, I'm going to write it as, if you look at, I'm going to blow it up. And if you look at here, 92 proton with 0 proton, and is emitted by the beta ray, which is a -1. So you need a 93 proton on the X side. Okay? So I can write 93, and if you look at the periodic table, that's a neptunium, so MP. And so you can write this characters in red, and then finally you figure out 238 plus 1 is 239, and this side is 239. So this is a 239, 93 Neptune. So that's the one that X is going to be here. And when the Neptune is being generated from the uranium, right? So uranium is hit by the neutron, you generate the Neptune, and with the electrons are coming out, that Neptune is decomposed into making another electron, or the beta ray coming out, and then they make this compound Y. That compound Y is really the main product of the breeder reaction, which is a nuclear reaction. So let's figure that out. So the Neptune 93 atomic mass with the whole atomic number 93, atomic mass 239. Now decompose, and they are saying that this reaction tell me that electrons are being emitted. Beta ray is emitted. So I'm going to write this -1 and 0 on this side, and then I fill the gap. Okay, -1 is here, and 93 here. Supposedly, so the Y species must have atomic number of proton to be 94. And then if you look at the periodic table, atomic number 94 is a plutonium. And then you look at the you also do the mass balance, and that's a 239 is for the plutonium isotope mass. And this is essentially what is being used in the atomic bomb for the plutonium bomb. So you can make the uranium with this, the neutron-based reactions. You can make this enrich the plutonium. This is actually man-made, more or less a man-made atoms, and then but that's a one that has been made by this reaction. So not all the elements in the periodic tables are the naturally occurring. Some of them are actually man-made. Number 11 problem is so easy. This is a problem, say, what particle described as a symbol of, I guess, almost no charges, but same charges as the proton. That's what we call the positron. We are using the beta plus as a symbol, and so you just look for the answer for the positron. My answers are being highlighted already as a red because I want to make sure that I got the correct answers, and then I have a answer key, and I want to compare that. So this is sometimes actually the answer keys are incorrect, and I discuss with the instructor in the class and to make sure that we can correct the answer keys. So I just show the answers right up front and then see how I'm doing it here. Okay, so the polonium, the third problem is a polonium 214, and I look at the periodic table polonium. And if you remember to seeing the polonium here, that's where it is, and that's an 84. So then 84 is a polonium. So I'm going to write polonium with an 84 atomic number, and the 214 is an atomic mass. And then they said it transformed into the lead. So this one is a practice for you to say lead, and you can look at the periodic table, and then looking at here, that's called the lead. And then atomic number is 82. So you can write 82 atomic number lead, and then 210, they said 210 is the atomic mass. So you need to finish up this balancing. The number of proton has to be balanced. So 2 extra proton has to be come out, and then from polonium, and the 214 atomic mass. Now 210. So therefore 4 is an atomic mass for this particle. So atomic mass 4, number of proton 2. That's what we call the alpha particle. So this is an alpha particle emission. So that's why it's called alpha emission from the polonium, right? So a reactant nucleus. So the answer is C. So I have solved this problem so far. And then here, and then this is a 3 problem set that I need to solve before I go back to this, the transition metal catalyst problems and so on. But because I have an extra time that I want to spend the time a little bit here to give an overview, and I don't mind to solving again in my evening class on Thursday. Okay, so this one is ytterbium, and the ytterbium is actually the symbol is a YB, and the thing is about they give you a half-life is 101 hour, and immediately you need to look up your reference sheet. Okay, so I'll find the reference sheet, and so then you can see that. Okay, this is the first order decay, and that's also the first order decay, the half-life versus the rate constant equation. So you're gonna copy, write it down. Half-life is K ln 2 over K. And so that's something that you have an information about K once you know your half-life. And then this is a 101 hour. So therefore, you know your K is essentially ln 2 divided by 101, and their unit is 1 over an hour. Okay, so I go there, turn off the light. Okay, and then how long would it take? So they want to figure out what is a T, and if the isotope decay to exact 1/5 of its original value. So what that means is your A concentration is now 1/5 of original value, A naught, and then that's equation is A naught exponential minus KT. Okay, so this is a first order reaction that you can use it for, and that will be essentially ln 5, the same as a KT, and then you can plug it in the K value. You can find the T values from here. So that's a logistics from here. There are many versions of the first order decay reaction. This is one of the versions that you can use that, and I have also discussed another version, which is a natural log ratio between the original concentration and the at time t concentration. So that's something that you should know. And I want to talk about, because we talk about the value of stability, and this problem is actually quite interesting and is a little bit involved. So let me cover that, and then we can close for the day. The number 15 is a pretty similar problem. If you read it, it just you can solve it by essentially calculating the discrepancy in AMU unit. It's a little bit different problem than before, but you will see in my other videos. So this one, I just wanted to recap on what I just said before. If you remember, this is what was a figure before. We use a symbol number of neutron, number of proton, and our reference line was, okay, N over Z is 1. That's the same number of protons, same number of neutrons. And what is called the value of, what do you call the value of stability? Okay, so the value of stability is kind of follow this line, and they kind of deviates onto here, right? So this is where the nature prefers. So so what that means is anywhere is not in the value of this stability region, they want to have something happens. And then they say nucleotide above the value of stability. So quote unquote above the value of stability. So what that means is you are here. That's what means a value of stability, and you are above that. And so for that, I want to go to be here because you are unhappy too, but you want to be happy right here, right? So to do that, you want to increase. So this one increase the number of proton, right? So if what that means is x goes to y, but your number of proton is, let's say it was z, but now you wanted to make it z plus 1. And how they make it happen? Because you want to have a minus 1. You can keep this one as same as before. So this is a 1 to make your z number goes up, which is we are moving the z increasing direction in this way, right? So then this is related to the beta emission. I want to also mention to you that in the previous exam, actually, they give you an example of some kind of elements like here. This one is actually wants to go the other way, which is they want to actually decrease, right? Decrease the number of protons. And how do they do? By doing the electron capture. Okay, so this is another example that they ask the same question in the same different way, and make sure that you understand where they are unhappy atom because they have I guess they have more neutron than they need. So the way that you can kind of make it happen is by making more neutrons, by making more protons, so that you can have this locating yourself in the valley of stability. Okay, I think that's said it good enough, and I think the